And similar to the continuous time case, we can also look at the mixtures of two complex sinusoids. Right. Now, if you observe each one of these sinusoids, right, we can see that this first one is periodic with period 3, right? And this one is periodic with period 8. Now, when you combine two periodic signals, right? So for a signal to be periodic, it means that this signal starts to repeat itself after 3 samples, right? It behaves the same every integer multiple of 3. And this signal behaves the same every integer multiple of 8, okay? So when you mix them together, what you have then is, again, a periodic signal, but a signal that repeats itself after integer multiples of both 3 and 8, okay? So the period of this signal xn is then the largest common multiple of 3 and 8. So the period of xn is the largest common multiple of n1 and n2, which is 24. 你说哪一个东西？你说什么？你说它是什么？因为你的在 discrete time 你的那个 period 一定要是一个整数嘛，因为你的 index 都整数，对。对，所以像这一个的话，它的 frequency 是 right. So if you look at the signal, the omega naught over 2 pi is 3 over 8, right? So 3 over 8, right? If you view this as the factor m over n, right? M over n, right? We mentioned here that, you know, if omega naught over 2 pi is m over n, where m and n are coprime, then the period is just n, which is 8, okay? Okay. So basically what this is saying is that in order to return back to the same point, you need to take 8 samples covering 3 periods of the continuous time sinusoid in order to come back to the same point, okay? So you take 8 samples over 3 replicas of the continuous time signal in order to come back to the same point, okay? Now, also similar to the continuous time case, we can also define, you know, harmonically related periodic exponentials as exponentials with a common period capital N, okay? Now, we know that for a signal to be periodic with period capital N, this means that, you know, omega naught capital N must be some integer multiple of k, which means that omega naught must be 2 pi k over capital N, okay? So for a complex sinusoid to have period capital N, its frequency must be an integer multiple of 2 pi over capital N, okay? So this is, you know, very much like before. So this is very much like the continuous time case where omega naught here is 2 pi over t naught, okay? But the key difference here is that, you know, if you look at, so however, if you look at phi sub k plus capital N, right, which is e to the j k plus capital N 2 pi over n times n, is equal to e to the j, e to the j k 2 pi over capital N times e to the j 2 pi n. Okay? So if you multiply this inside, you get k 2 pi capital N times n, and you multiply this, capital N cancels out, you get 2 pi n. Okay? So you can see that this term is 1, right? So this is just e to the j k 2 pi capital N n, and this is exactly the definition of phi k n. Okay? So what this is saying is that this complex exponential phi k plus capital N is actually exactly the same as phi k. Okay? So previously in continuous time, the set of harmonically related complex exponentials, is infinitely large, right? For any integer k, you're able to obtain a different harmonically related complex exponential. But in the discrete time case, the number of harmonically related complex exponentials are actually finite, because after you increase k by over capital N, you start to repeat yourself. Okay? So the conclusion is that there are only capital N distinct harmonically related periodic exponentials.